Now we're going to look at this problem. The rod AB rotates about the point A, and rod AB is pushed by DC, and AB gets an angular velocity omega. Find an equation that rates the velocity V to angular velocity omega of rod AB. So this rod DC is pushing AB, and so AB is rotating and is pushing with some kind of velocity in this direction. And we want to find an equation that relates the velocity to the angular velocity. So we have a picture something like this, and we want to relate these values here. Now we know that this is pushing at some velocity. So some velocity in this direction. And it's pushing this rod. And we would like to somehow relate all these values here. Now, one thing to notice is that this rod moves in this direction to the right, X will decrease in length by the same amount that this rod up here increases in length. So keep that in mind. That's very important when we calculate this. X is decreasing. This dimension X is decreasing at the same rate this is increasing, because as this is getting pushed in this direction, you can see that as this increases, X decreases. So let's see if we can find some kind of relationship. So let's focus on this little triangle here. We have theta here. And so this is 2 feet. This is X here. And so let's see if there's a way we could relate this theta to X. And of course, the simplest way is to say the tangent of theta, it of course is equal to opposite over adjacent, like this. Then we can rewrite this as 2 over tangent theta. Now, since tangent's in the denominator, we could work with cotangent, make that x equal to cotangent, but sometimes that's a little bit hard to work with. So, but of course, tangent is sine over cosine. But if it's in the denominator, we can write this as x equal to, and then again, sine over cosine down here. When you flip it up, it'll be cosine over sine, like this. Now let's take the derivative of this. See, if we take the derivative on the left, again, we're taking implicit derivatives. So now if we take the derivative, again, I can bring that 2 in front. And we have a quotient here. Again, we're taking the implicit derivative. So the derivative of the numerator will be negative sine theta times theta dot, because we're taking the derivative of that, times the denominator minus the numerator times the derivative of the denominator, which will be cos theta theta dot. over sine squared theta. Remember, quotient rule says we have to square the denominator. Now, if we go through here, we can factor out the 2 theta dot, and I'll factor it to negative. And then we're left with sine squared theta, cos squared theta over sine squared theta. And the numerator, that would be just 1. Like this. And so what we have now, a couple things. Notice, of course, theta dot is the same as omega. And this, we said that this is getting shorter at the same rate that this is being pushed forward, except as this is increasing, this is going to be decreasing. So these are going to be like opposite signs. This velocity here decreasing is going to be the same as this velocity, but opposite signs. So we can put this velocity in here, except that'll be a negative v. Like I say, we can put omega here, like this. And then finally, if we multiply by -1, so the velocity is equal to 2 omega sine squared theta. And again, we said we were trying to relate this angular velocity here to this velocity, and that's what we did. And of course, you can use this equation for any theta. And so if you know a theta and you know your angular velocity, you can find v, or if you know v and theta, you can find omega. Take a look at this problem. At the instant shown, theta is 60 degrees. The slide guide is moving to the left with an acceleration of 2 meters per second squared and a velocity of 5 meters per second. Find the angular velocity and acceleration of the length AB at that instant. So let's take a look at this. So our problem looks like this. And so this mechanism is moving to the left. And so we need to relate some of these values. Now, notice one thing similar to other problems. Notice as this is increasing, this dimension here is decreasing. In fact, we can probably call this x if we want right here. And again, this is getting bigger at the same rate. This will be getting smaller. So again, let's take a look at this little triangle here. And let's call this, that maybe x. Let's may call this y. And you can name these whatever you want. And now let's relate x to this angle. So we could say x is equal to 0.2 cos theta, because x is adjacent to theta. Then again, if we take the time derivative, Again, the derivative of this is negative 0.2 sine theta. And again, because we need the implicit derivative, we'll have to put a theta dot. And we'll maybe call this equation 1. Take another derivative, x double dot. Again, the derivative of the first. And again, we'd have to do the implicit derivative here. So we're going to have a theta dot. Remember, we're taking like the derivative of this, but we don't know what that function of t is. So we'll have to put a theta dot here. So that's the derivative of the first times the second plus the first, which is this here, times the second, like that. Excuse me, times the derivative of the second, should be like that. So again, the derivative of the first, which is that, times the second, plus the first times the derivative of the second. And we could simplify this maybe just slightly. We could maybe put a couple of these together. This would be minus 0.2 cos theta, theta dot squared, minus 0.2 sine theta, theta double dot, like this. You may call this equation 2. Like this. So now, if we want to find, let's see, we're asked to find, angular velocity and angular acceleration. So we could use this equation here. So this is like the velocity of x. And so notice, as I mentioned before, it's decreasing at the same rate this is increasing. So if we use equation 1, and put our value here. And now, since it's going in the opposite direction of this, so in other words, is this is increasing, this is decreasing, we can say this is going to be negative. So it's going to be negative 5 meters per second. And that's equal to minus 0.2 sine. And we're told that it's at 60 degrees, I believe. Yes, 60 degrees. And you could change that to radians if you had wanted to. And theta dot is here. And put that in your calculator. And we get theta dot to be 28.87 radians per second. Now, to find the angular acceleration, we can use equation 2. And I'll use this version here. So we're going to have, and again, for equation 2, now here we know the acceleration is 2 meters per second squared. So we can put that over here again, except the fact that this is shortening at the same rate at which this is increasing. So over here, we'll put negative 2 meters per second squared. And then over here, we'll have negative 0.2 cos 60 degrees. And theta dot here, we just found theta dot, so we can plug that in. Minus 0.2 sine 60 degrees, theta double dot. And I realized I forgot to put the square here. That should be squared. Again, that was our theta dot squared. 0.5. So let's put that in our calculator. And when I put that in my calculator, got something like theta double dot is equal to negative 469.7 radians per second squared, like this. Again, I may have rounded something, so you might have got something slightly different. Again, so there we have it. Much like the other problems, we always want to relate some of these items here, which we did here. We related x to theta, took derivatives, and realized we had the velocity x dot. We had the acceleration x double dot, plugged them in, and found our values. So let's take a look at this problem. In the diagram below, rod EF may move vertically, and rod CD may move horizontally. The crank AB rotates with a constant angular velocity of 10 radians per second. Determine the velocity acceleration of CD at the instant theta is 30 degrees. Determine the velocity acceleration of rod EF at the instant theta is 30 degrees. So let's take a look at these. Now, again, one thing to notice is as this goes to the left, this side, this dimension will get smaller. And as this goes down, this dimension will get smaller. Let me actually make another little diagram here. Let me make something like this. And let me call this theta. And we know this is 3 feet here. And call this X, call this Y. And again, let's say if CD is going this direction, let's say velocity CD is say in that direction, then as CD gets bigger, X gets shorter. And also for EF, if we think of down to be like the direction of EF increasing, notice as this goes down, Y gets shorter. So we can maybe make some relationships here. Let's start with this X right here. Start with the relationship here. So we can relate X to theta very easily. So we can call X equal 3 cos theta. And then take derivatives. Theta dot derivative here is going to be negative 3 sine theta. Then again, this is implicit derivative. So it'll be the derivative inside has that. Then we'll have second derivative, derivative of the first. Again, that's the derivative of the first right there, times the second, plus the first, times the derivative of the second, like this. And we could put these theta dots together just to make it look kind of nice. Minus 3 cos theta, theta dot squared, minus 3 sine theta, theta double dot. So now let's apply what we have. We have theta dot. And now one thing to kind of notice here is that, again, CD is moving this way. So it's going to be opposite sine of X. So in other words, if X is shortening, this is going in the positive direction, etc. So we can replace, let's say, in this equation up here. Let me give these names. Let me call this equation 1, equation 2. Up here, I'm going to replace X dot with negative VCD, because again, this is the velocity of X, and this is the change in CD. That's going to be equal to 3 sine. And we want this whenever theta was 30 degrees. And again, up here, theta dot, we're told was 10 radians per second. And put this in your calculator, you're gonna get minus 15 feet per second. And so it's gonna be negative and negative. So VCD is going to be 15 feet per second. And again, that means it's increasing that much to the left. Then for the other equation, look at equation 2. Once again, as this is accelerating, this is going in this to the left in the same amount. So it's shortening. So once again, over here, we can replace, again, using equation 2. On the left-hand side, replace that with the acceleration, ACD, negative 3 cos 30 degrees, 10 squared, minus 3 sine theta. Now, theta double dot is 0. Remember, we have constant angular velocity, so it's just going to be 0. So we work this all out. We get negative ACD is equal, and this comes out to be negative 259.8 feet per second squared. And so this is 259.8 feet per second squared. Again, that's acceleration to the left. Now let's do the same thing for the y direction. In fact, let me just make another little picture here real quickly. We have theta B feet, Y, X, V, E, F going down like this. And so let's see if we can relate Y, because again, whatever this is going down, Y is going to be decreasing. So again, let's relate Y to theta. Y equal, again, that's going to be sine because they're opposite. So that's going to be 3 sine theta. Once again, take derivatives implicitly. So this is going to be 3 cos theta. Since it's an implicit derivative, we'll do that. Now take the derivative to the first. Like this times the second. Plus the first. Times the derivative to the second. Once again, let me just give these names. Call this equation 1, equation 2. So again, use equation 1. Now, once again, as this is going down, this is going to shorten. So if we keep these the same, so in other words, let's see, if we call this negative, I don't know what if you call this the negative direction, I'm not sure. So I would say maybe since this is like increasing, we'll consider that positive, and it's opposite of this, which is shortening. So again, if we use equation 1 here, this is going to be VEF equal 3 cos 30 degrees. (25.98 feet per second). So in other words, I just plug the numbers in to here, and I got 259.98. And that would be, again, if this is assuming this is going in this direction. And then also for the acceleration, use this equation here. Once again, I'll go AEF. It's going to be minus 3 sine 30 degrees. And then over here, we have theta dot squared. So that'll be 10 squared plus 3 cos 30 degrees. Now again, theta double dot is 0 because remember, we have a constant angular velocity. So that's going to be 0. And if you put all this in your calculator, this comes out to be negative 300 times a half. So this will be negative 150 feet per second squared. Now look at these. I probably, thinking of this, I probably should have written this VEF going upward. like this, because what we end up having here, the way I kind of wrote this, is that this is going to be y dot, and clearly if the omega is going this way, y dot is going to be increasing, and VEF would be going in that direction. So we can say that's going to be upward. And now since this is negative, that's indicating that the acceleration is going to be downward. So it's going to be AEF 150 feet per second squared downward, like that.